Okay, this video is going to be about experiment number 5, RLC circuits in series resonance. So let me share my circuit maker screen with you. And it's not doing it. Share the screen. Here we go. And what you can see is a circuit over on the left-hand side. It's got a 10 microhenry inductor and a 0.1 microfarad capacitor, and it's got a load resistor R1 of 47 ohms. So let's just think for a second what's going to happen here. The capacitors we already talked about in a prior experiment, at low frequencies, this thing will have an infinite resistance or reactance to the AC signal. The inductor at low frequencies will have low or zero reactance to the AC signal. And then they flip. That is, we go to real high frequencies, the capacitor acts like a short, the inductor starts to act like an open. However, there's some frequency in between the extremes of 0 hertz and infinity hertz that the reactance of the inductor and capacitor are equal. And since they are opposite in phase, 180 degrees out of phase, they cancel out. And at that point, the combination of the series pair of them will look like a short circuit, and everything that you apply will appear on the output. So for low frequencies, the capacitor will predominate and the phase angle will be determined by the capacitor. At high frequencies, the inductor will predominate and the phase angle will be predicted by the inductor. Remember, I like to talk about Eli the Iceman. That's ELI, voltage leads the current in an inductor, and the Iceman, ICE, current leads the voltage in a capacitor. So Eli, the voltage can change instantaneously, but the current cannot. The current changes as the magnetic field gets energized. In the capacitor, the current can change instantaneously, but the voltage cannot. The voltage will build up, in a charging curve, time constant type fashion. So let's take and hit the running man over here, and let's see what we have. This has been set up as a Bode plot using the Bode plot tool. You might notice for this one, takes a little bit of time to run the simulation. Got a lot of points, so let's see what happens. Here we go. We kind of jump right into the Bode plot, which shows I'm going to kill the voltmeter here. There is a transient oscilloscope there. We don't care about that guy. Let's get rid of him. Here we have the resonance curve of this particular circuit. It's a series resonant circuit. And if we want to know what the resonant frequency is, we could go here with A. It looks like it's about 158.5 kilohertz, somewhere around there. We could blow it up. But if we blow it up, we might just get a flat line here. Yeah, it's hard to see exactly where the highest output is. So let's go back. If we want to find the bandwidth of this thing doesn't have a very sharp, peak. It's probably a low Q circuit. Normally we talk about going to the, let's find B is over here, the -3 dB point, but another place we go is where the output falls down. The output's 1 here, and the output falls down to 70.7%. So let's put C. Well, we have to, the absolute value of C is 677. If we go up here, 706.7, not too bad. So we'll move A over here and B over here. And we get somewhere around A to B is a bandwidth of about 738 kilohertz. The resonant frequency we saw before was in the range of 150. So this thing has a Q of about 0.2 or something like that. Very unsharp resonance, we'll say. How could we sharpen that resonance up? Well, if we went back to the circuit, what happens is we'd have to lower this resistance. And, I could do that now, which is kind of maybe an interesting thing. Let's take and maybe take and edit this device. Let's make it 4.7 ohms. Hit OK. And it's not part of the experiment, but let's take and run this guy now. And again, it takes a little while to run, so we kind of hold our breath while it happens. Almost there. 70%, 80%, 90%. There we go. And right away, you notice that what's happened, the bandwidth that before was from A to B is now shrunk quite a bit. It would be actually now about from here to here. And let's see if I can get that closer a little bit. That's that one to move for me. Now it's down to like 75 kilohertz. So if the resonant frequency is about 150 kilohertz, and now the bandwidth is 75, we'd get a Q about 2. And of course, I lowered the resistance by a factor of 10. And as I said before, the Q is about 0.2. Now it's gone up to 2. And I could keep doing this if I take, let's do one more while we're at it. Let's go and change this guy to 0.47. And let's see if what happens here. If I go make this 0.47, now the Q should be up to a factor of about 20. And let's take a look at okay. We run it. And again, we hold our breath. 25%, 40%, 50%, 60%, 70%, 80% calculated, 90%, and finally 100% calculated. Oh, here we go. Here is our frequency response, and see how we have a very sharp frequency response at this point. And it'd be actually tough to take and measure what the Q is here, because the bandwidth would be tough to ascertain. We'd be probably better off now to take and change our simulation, our analysis points. It's called, well, we can't do it while it's running. If I was to take the simulation and change the analysis setup, if I go from a start frequency of, say, let's go add a couple zeros to that. And let's take and get rid of a couple zeros here. Okay, run the analysis. And I've lowered the bandwidth of what the Bodie plot's looking at. Didn't do too much for the, still doing the same number of points. I didn't change those. So we're still 75% now, 90 and 100% done. However, our curve is a little more manageable now. We go 10 kilohertz to 1 megahertz, and we can actually see a little bit more of what's going on. We could probably figure out the bandwidth without too much problem now at this point. Okay, so that's it for experiment number 5.